That's great. Thank you, Studio
Okay,
B.
so ladies and gentlemen, welcome to the show. My name is Diamond, and I am the host of Cosmic Catastrophe on Revolution Radio. We had some technical difficulties, but we've seemed to have Studio B helped us iron those out. And let me just make sure we are recording. Yes, we are.
We
We have a
are.
great show in store for you, even though we had some technical difficulties. Joining us today is my lovely co-host, Leah Shaper,
Hello.
and you're not echoing anymore.
No, I'm not. Neither are you. We no longer sound like we're in a ravine somewhere.
We've got two interesting papers we're going to talk about today of very differing disciplines. We're going to start with an article that came out, or a paper, that our sun may be overdue for a superflare. In the second half of the show, we're going to tackle some Neanderthal genetics. And apparently, the Neanderthal gene flow into Homo sapiens occurred in a very limited time period, 7,000 years, between 50,500 and 43,500 years. And this corresponds to one of the most rapid shifts in our magnetic field in the last million years.
Oh, that's interesting.
So we'll go over all of those details and more. Welcome to the show. All right. Anything you want to add before I share the screen?
Nope.
So, what is a superflare? That's a good question. Do you have an answer?
Well, that's actually one of the things I wanted to bring up, right? Because this paper defines superflares essentially by magnitude, right? So something that's on the order of 10 to the 34th ergs or larger, which would exclude the Carrington event in 1859 because that was probably only 10 to the 32nd,
Yeah.
which
So, the
is
Carrington event, if it was X 40 or let's say X 100, this superflare is two magnitudes greater. So, that takes it to X 10,000 is the beginning of superflare, because it goes up once you go to 30 to the 33rd ergs, you're talking X 1000. When you go to the X to the 34th ergs, that is X 10,000, which
right.
is unimaginable. I mean,
Well,
what we would all, the surface of the earth would melt.
right. Right. And so maybe that is what happened to Mars, right? But what about us? Which would also then suggest that in our solar system that this conclusion of this paper isn't really true. But I'm a little bit confused because they as I see it, drawing that line at 10 to the 34th is potentially a bit arbitrary. And if I'm reading this correctly, they seem to suggest that the frequency of superflares on stars in general be about the same for our sun, but at a lower energy level.
Yeah, and I think I can agree with that. Let's go over what the paper says in the abstract. Solar flares are bright, transient, multi wavelength emission from active regions of the sun. The most intense directly observed solar flares release energies of 10 to the 32nd ergs. So, what the directly observed, they're talking about Carrington.
Right.
It's unclear whether the sun can produce more intense flares than that or how often they may occur. So, what this team did is they went out and investigated brightness measurements of 56,000 sun like stars observed by the Kepler Space Telescope. And they identified almost 3,000 bright stellar flares with energies 10 to the 34th to 10 to the 35th. That is an X 100,000.
That's insane.
But now these stars, these are sun-like stars. There's a huge group of them.
Well, this is the other thing that's really tricky, and it is acknowledged in this paper, but they're looking at okay, one of the things that they did differently from previous studies that tried to figure this out was that they included which is it? They included, so they looked at the rotation rates of stars, sort of using that to categorize the stars as being like our sun or not. And in this case, they included the previous studies were limited to stars with known rotation periods. However, the majority of stars with measurable rotation periods are much more variable than the sun, potentially biasing the results. So, they basically broadened the range of stars that they were looking at. So they looked at stars with similar magnitude, but I again, the categorization seems a bit arbitrary to me. And then the other problem is that out of the 56,000 stars that they looked at, they observed, I don't remember what the exact number is, but 2,000 and change super flares on
2,889 superflares on 2,527 sun-like stars. And this is out of the 56,450 that they observed. So that would
right.
mean 5% of sun-like stars can flare at this magnitude.
Right, but so the problem is like, okay, is it the case that those 2,527 sun-like stars, are they somehow different than the other 50, 51,000 stars? Right, and they acknowledge that here. They say we cannot exclude the possibility that there is an inherent difference between flaring and non-flaring stars that was not accounted for in our selection criteria.
Yeah, because the resolution of looking at these stars is very low. So they're looking at their brightness. We have very few stellar systems we're even aware of as far as the planetary composition of the solar system.
Yeah.
So when we're looking at these stars, we don't know if there are other smaller stars in close proximity that are not visible. And that is the explanation for a micronova, where you've
Right.
got a small, super dense star very close to a sun-like star, and it is sucking in material off of it, causing it to flare. So
Right.
the problem is we don't have, I don't think, the resolution to know the difference in these stars. The only way we're determining it in this paper is relative brightness. So we'll just get a bunch of stars that are the same brightness and we'll look at them.
There was actually one other variable that I'm forgetting now. It wasn't just the magnitude, it was something else also. Oh, it was temperature as well. So similar temperature range, 5 to 6,000 K. But to your point of what you were just saying, they also acknowledge the issue of that approximately 30% of flaring stars are known to have a binary companion.
Okay, so
And acknowledge that
30%.
that may contribute to the flaring, right? We don't even know if we are part of a binary system, and we may be.
Yeah.
So I think there's only limited conclusions that you can draw from this. I mean, it's interesting, but I feel like the cutoff for what constitutes a super flare is a bit arbitrary and maybe not being applied consistently across stars, to my reading of this. And we don't really know enough about the particulars of all of the stars that were looked at and how they might be different from each other.
Yeah, and I think our solar system might be trinary.
That could also be the case.
Because there is historical evidence that ancient cultures revered Sirius.
Right.
And also, we now have the information on Barnard's star.
Right.
Barnard's star is what appears to be in a 24 to 26,000 year cycle with our sun. And we really don't know much about Sirius. I think it needs to be more study on that. And we may be in a more complex. It's definitely Occam's razor. The system is probably more complex than we make it out to be. We're talking about very complex systems.
Right. Well, and consider also that, okay, so all of this is to extrapolate a frequency of flaring of sun-like stars. And it's looking at trying to establish a consistent frequency of flaring. But consider that, okay, if, say, for example, we're in a binary system with Barnard's star, well, if we're going to be experiencing a lot of flaring due to interaction with another star, that's going to happen when we're in close proximity to Barnard's, not right now. So the frequency isn't going to be consistent across time.
Right. And it has to be very close. We're talking less than a light year. It has to be in close proximity for the electromagnetics to mingle.
Right.
There may be very large scale Birkeland currents, But if you're talking very long distances, the amount of energy is probably much weaker. I'm not a specialist in the field. There may be no loss of energy through a Birkeland current for all I know.
Right. Yeah, there's a lot of stuff we don't know here. And like you said, it appears to be very complex and we really barely have a grasp. I mean, it's hard enough for us to even find these flares, right? They developed a particular technique to identify the flares that is different than what's been done in the past. And you know, that of course has yet to be sort of validated as a validated as a valid method of determining where the flares are.
Yeah, and they looked at almost 60,000 stars. Less than 3,000 were flaring, super flares, which means it's good news that most sun-like stars do not flare at this level.
Right.
We also know that 30% of them need another star in close proximity. 30% of the 5% are not like our solar system, which makes our solar system even less susceptible to super flaring. Additionally, we have high resolution data throughout the ice ages in the form of ice core data, right? Going back over almost 1 million years of high resolution ice, and there's no evidence of super flaring. So if these are happening in a centennial scale, they're certainly not happening here in our solar system.
Well, right,
what
and
we
that's
do
the other
know
thing.
is Miyake events are occurring, right?
Well, so I was about to say that, right?
They
'Cause
occur about every 2,000 years.
Right. And they acknowledge here solar energetic particle events, you know, and there hasn't been a correlation between super flares and this. And also I have to go back to this thing where it seems like the energy level of a super flare seems a bit arbitrary. Like, okay, you know, if we're talking about what was it, an X 100,000? Is that what you said? 10,000?
An X. So when you say 10 to the 32nd, that's an X100. 10 to the 33rd is X1000.
Yeah.
10 to the 34th,
34th
is 10,000. And they mentioned seeing an X to the 25th super flare, which is X100,000.
You mean 35th?
To the 35th, yeah.
Yeah.
That would be an X100,000. That would probably look like this picture on the screen. It would be that severe.
Well, and that's the thing. I mean, like, if that happened, like you said, Earth would be fried, right? Like that would probably blow our atmosphere away. So, well, Earth is still here. It's been here for 4.5 billion years, and that clearly hasn't happened. So, and that's the other thing. So, what it looks like is going to very much depend on let's say, a planet's distance from its star. So, yeah, the title of the media article that goes with this, you know, claiming that we're overdue for super flare, and that, you know, coming to this conclusion that they should occur every 100 years, I find that very deceiving, because again, it doesn't account for that this may not be a consistent frequency over time.
Well, and
what constitutes as a super flare from one system to another may be different.
But what we know is that our sun doesn't do that.
Apparently not.
We have the ice core data, and there's no evidence of it. There's evidence of Miyake events, but these events that even these events are just 100 times greater than the Carrington event. So it's not even in the super flare category. It's between the Carrington event and a super flare, right in the middle, the Miyake events.
Yeah.
And clearly we know they don't fry Earth. So that is more of a cascading radiation event rather than a CME, in my opinion.
Right.
So it's not a coronal mass ejection that causes these Miyake events, because we've studied the historical accounts of them. No one witnessed anything in the sky. If they were an X1000 CME and solar storm, they would light up the aurora for months. Right. And it would never get dark. And that hasn't happened historically. We only know of the Carrington event. It did do that for a few days. If it were to happen today, just a small event like the Carrington event, we are back in the Stone Age.
Yeah. Yeah.
And the most of the population will die. It would be a catastrophe. But the good news is AI won't take over the world and we won't all die at the hands of robots.
You know, I just want to throw out there too that this paper, while I find it interesting and it raises a lot of questions, one of the things that it brings up is, and we've talked about this many times on this show, you and I are not entirely convinced that astrophysicists know what the heck they're talking about. So, there's a variety of ways discussed in this paper in which stars maybe can be categorized, right? Talking about their rate of rotation, for example, how variable they are. One of the things it mentions is this idea that stars that rotate faster are younger, and that our star is slower by comparison, but I'm not convinced that we really know that that's true, right? So we're trying to categorize stars based on some ideas that we have, but I don't know that those categorizations are actually meaningful, or that they mean what astrophysicists think they mean, you
Yeah, I
know
agree.
so it just becomes really hard to come to any firm conclusions when you're trying to study something like this.
Right. And the fact that Live Science's headline is so disingenuous, the
Yeah.
paper specifically says we've only observed certain flaring on Earth well below the superflare level, and
Mhm.
yet they write this headline.
Well, actually, you should blame the paper too, because the title of the paper is Sun-like Stars Produce Superflares Roughly Once per Century. That's misleading,
It is.
because that's not really the conclusion you can draw. I mean, yes, you could do the math and say that, but it doesn't mean necessarily what you think it means. It doesn't
Yeah, because
necessarily mean.
only 5%. It should say 5% of sun-like stars produce superflares once every 100 years.
Well, no, I think it's based on the 5% that they looked at, that they took that and they extrapolated that to mean once per century. They're not
Yeah, but the
watching.
other 95% don't flare, so that's a lie.
Right, but so they're taking, right, they're taking the 2500 within the 5600 and using all of that math to say once per century, but that's not necessarily the case at all.
So
It
the
may be that
conclusion,
only those stars are flaring, that it has nothing to do with the time frequency.
well, the conclusion here is that our sun never does this and won't be doing it on a 100-year timescale.
Not as far as, well, certainly not on a 100-year time scale. And
But
we have no
what we
known
do know
record of it doing it at
historically is
all.
that Carrington type events, and we had a paper on here, occur every 150 years, which means the next one is happening now.
Right. I mean, it could be that, what constitutes a super flare for any particular star varies tremendously in magnitude, right? And in the case of our sun, that the magnitude is much lower, and maybe we do have a super flare every 150 years. It's just not 10 to the 34th. It's more like 10 to the 32nd.
I like it.
And they do kind of say that in here. So that's the other thing that I find a bit confusing about this paper.
All right. So, how do solar flares disrupt technology on Earth? They destroy it. Particles batter the Earth's magnetic field, usually 8 to 18 hours after a huge event. It's very rapid when it gets to Earth. And these changes to the field cause huge surges or power jumps and failures in the electric grid. This is due to currents flowing, telluric currents increasing, flowing through the Earth. And because our planet is covered with power lines, this energy is going to start to transverse into these lines. And anything that is conductive will be electrified. So
Yeah.
it would be a cascading catastrophe. Things would explode, cities would light on fire, and many people would starve in the first few months.
Right. Well, yeah. And that certainly could occur with a Carrington event, as we've discussed.
Yeah, so don't be scared. Be prepared for some event like that, you know?
And as you rightly point out, the upside is that the AI will not be taking over if all of our technology is down by this, which in that respect, I feel like it can't come fast enough.
Right. And make sure you know how to get clean water and food, and you can
Right.
make it, and
Right.
shelter and heat.
Maybe all the drones are launched by AI.
Yeah, that's why we're so confused.
Why we can't shut them down or even approach them.
All right, let's talk about Neanderthal genes. Now, for the last decade or so, we've known since about 2010, when we sequenced the first Neanderthal genome, that humans have Neanderthal genes.
Mm-hmm.
What's interesting is Homo sapiens that were alive at the Lachamp magnetic excursion 41,500 years ago, they've done some genetic sequencing on those.
You're frozen. Are you there?
Neanderthal DNA. But today, it's less than 3.
I missed a little bit of what you were saying because you froze.
Oh, well, at the Lachamp magnetic excursion was the peak amount of Neanderthal DNA in Homo sapiens. It was between 7 and 9%. And today we're down to about 3%.
I thought it was 2. Yeah, but regardless,
yeah,
quite a small
below 3.
amount.
I know that.
Yeah.
So all of this mixing occurred basically in Europe and in Asia over a period of time. We've known that Homo sapiens had been mixing with other hominids for about 100,000 years.
Yeah.
But it's interesting, we didn't know to what extent until recent scientific breakthroughs allowed for this study. And what this study showed was a gene flow that occurred for a 7,000-year period. And the time was between 50,500 and 43,500 years ago.
I'll throw in there that there's another paper that comes to a very similar conclusion, except that the time frame is like for like a 4,000-year period, but in the same time frame.
Yeah. And then it says around 43,500, Neanderthals started disappearing. Yeah, because by 41,500, they were all gone.
Yeah.
And so we'll leave you a link to the paper here, Neanderthal Ancestry Through Time, Insights from Genomes of Ancient and Present-Day Humans. Okay, I got to load some pages. Do you have anything amazing that strikes you from the paper?
You know, I found this a little challenging to digest because the Neanderthal gene flow is sort of persistently compared with what they're calling like the early out of Africa group. Right. And they're treating the early out of Africa group as the main set of genes that all anatomically modern humans have. So, and I have big problems with the out of Africa hypothesis.
Well, you don't have to, you could throw that away here because we're just talking about Homo sapien genetics. So who cares where they think they came from? It's really not an issue when we're talking about this type of gene flow. The story may be wrong, but doesn't matter if the Homo sapiens are in Africa or Europe or Asia, they're still Homo sapiens.
Yeah.
You know what I'm saying? So the out of Africa theory, those hominids are not Homo sapiens. The out of Africa theory is pre-Homo erectus. It starts with Australopithecus is out of Africa. So this is way after that nonsense story. We're just talking.
No, what they're talking about is the group that left and went to Europe and intermingled with the Neanderthals. So they're talking about a much later period.
Yeah, because modern humans didn't enter Europe until about 70,000 years ago.
Right.
That's the first evidence of Homo sapiens there.
Yeah.
So we were somewhere else, not necessarily Africa. It doesn't matter. We could have come from the North Pole, but we didn't enter Europe and mix with Neanderthals in Europe and Asia until about 70,000 years ago.
Right.
Whether Homo sapiens evolved in Africa, it doesn't matter. They show up in Europe at 70,000 years ago and start mingling with at least 5 other hominid species. So, from 100,000 to the Lachamp event, there's at least 6 hominid species in Europe and in Asia.
Mm-hmm.
And in the paper, it says we're now down to 1% to 2% of Neanderthal genetics.
Well, that's for most people. And there are actually groups of people that still have more like 6% Neanderthal DNA.
Is that a specific race?
I can't remember, but I want to say that's in Asia.
Okay.
But don't quote me on that. That may not be entirely correct, but it is a specific geographical region. Um, and so if you scroll down a little bit, looking at this paper and this little, no, first page, bottom of the first page. So the you see
Here.
this go up a little bit, where it says 40,000 years, right? So this is where they're seeing the red part being Neanderthal DNA at 40,000 years, basically showing that there's a much higher percentage of Neanderthal DNA at 40,000 years ago than today.
The red being the expression of Neanderthal in these
Right,
graphics.
right. Which is interesting. I was asking myself a lot of questions about, like, well, does this preclude the idea that there was Neanderthal mixing at some point previous to this? And they do acknowledge that at least in some places there was potentially like a first and second pulse of Neanderthal genome entry into modern humans. Um, I just, it's hard. It's a little hard for me to digest, partially because I don't have enough background knowledge in analyzing genomes.
Well, the paper, I think, alludes to the fact that those earlier mixing, so we were mixing with Neanderthals probably for 100,000, maybe longer, 120.
Mhm.
But there's none of that is left over.
Well,
It
right.
appears as if something happened 50,500 years ago that we were mixing again, and that was important.
Well, and more interestingly too, they say that, so the specimens that they're looking at from this time frame, those people are not our direct ancestors, but we are related to them. So it's like we're the last. I don't even know. I'm having a very hard time articulating my thoughts about this paper because I had a lot of different thoughts and a lot of questions that surfaced when I read this.
Well, the conclusion you can come to is the only reason that there are non-African people on Earth is because of this 7,000 year period, which we're going to get to was a very tumultuous time on Earth.
Right. But so then, like, okay, that in and of itself, like, I don't think that's the only reason that there are non-African people on Earth. Because, okay, think about it this way. If as non-Africans, if our Neanderthal DNA is down to 2% as of, from 40,000 years ago or 50,000 years ago, then how is it that we have different races of humans with different bone structure, like significantly different bone structure, different skin color? Like, we are still highly differentiated, I would presume, by mixing with other hominids. And yet we're claiming that the only reason that we exist as non-Africans is because of this tiny amount of Neanderthal DNA. Like, that doesn't make any sense to me.
Hmm. Well, I don't know
How did
how
we
else to
become
explain it.
so physically different? Huh?
Well, let's talk about that. Why do Asian people all look very similar, and why do African people look similar, and why do people in Ireland look similar?
Right.
The problem is, just like with anthropology, when you're calling the same group of people the Hopewell, the Adena, and the Fort Ancient, just because it spans 3,000 years, does not mean you are correct.
Mm-hmm.
And the problem with all these sciences, especially vertebrate paleontology in the form of hominids, is that they've screwed everything up. And what they're finding is that what they're calling Denisovan, which is in Asia, well, they're Homo sapiens. They called them Denisovans because they look different. They have higher brow ridges. They're happening at the same time. They just named a new species, Homo juluensis, called Homo
Of
bighead, which is Denisovan. And someone pointed
Denisovan
that
is
out.
probably a
They're just
subset.
making up names.
Right.
So I think the reason we have different races is because hominids in different areas stay there and develop differently than other areas. Over long periods of time, you get a whole group of people that looks different than another group of people for a number of reasons. The amount of sun, the type of food they get, the nutrients in the soil, etc. And so we are just at the very beginning of understanding what was happening 50,000 years ago.
Yeah.
There's all these different types of humans. They're trying to say they all came from one group in Africa, which is incorrect. It
Yeah.
appears as if there are dozens of types of hominids all over, and we just have like a piece of a finger bone of one of them and a skull fragment here. We've got a long way to go to figure out what's happening here. But from this genetic study, it clearly shows for a 7,000 year period of time, there was some significant mixing event, which has no explanation in the paper, but
Yeah.
I have an explanation for you.
Right,
So
but it's not the reason for all non-Africans, right? I mean, think about it this way, right? Lots of African Americans who have very dark skin are only like a couple of percentage actually African, right? Which is very interesting, right? Because it shows that even a very small amount of African DNA is likely to give you melanated skin, significantly melanated skin. So to suggest that, a mere 2% of Neanderthal DNA remaining creates Caucasian people, it doesn't make any sense, you know? But
no,
that's
not
the claim right
Caucasian, not
now.
Caucasian, non-African.
Okay, yeah, non-African, right?
Way
But I'm
different.
saying but obviously Caucasians are part of that non-African group,
Right.
right? So
So
it
are
just
Samoans and Chinese
yes. I'm just making the point
and
that
Indians from India.
it
So
it doesn't
these
well okay,
groups are
so it's even
all
worse, right? Based
what
on
I
what you're
just
saying.
described. These groups that we call races are what they're calling species because it's not true. Based on this genetic study, we can have sex with all of these species.
Hmm.
And so the definition of a species is you cannot do that. You cannot interbreed and have viable offspring. So the whole biological sciences needs to be re-looked at because what's happening 100,000 years ago is what they're calling 6 different hominid species. We are all having sex parties. Well, and I'm sure we're also warring. I mean, there's probably times
Right.
of conflict and times when you meet another group and you're interested because they got weird beads or clothes or dances. And it's because of this mixing that we made it across the Lechamp.
You know what's so
So if we
fascinating?
weren't the whole point of this, I think, if we weren't interbreeding with Neanderthals, we may not have made it.
Yes.
Yes.
Well, and there is, I mean, one of the things that this paper does point out, it's very obvious the gene variants that came from Neanderthal that provided some amount of advantage to us, and the things that did not becomes very clear in this.
Because of
Um,
the way they remain all the way down through till today in the same spots.
right, right.
Yeah.
But then the other element of this that's really fascinating, and it's not just hominids that you see this in, but it appears that through time, there has always been this sort of parallel evolution, let's say, of different hominids, which I find fascinating. Like, how is it that we have different hominids that pop up, and hominids all being very similar, but they're different types of those hominids? I mean, I find that alone very interesting because you see the same thing with animals, right? There's different species of elephants, let's say, that pop up, but yet they're evolving in parallel, you
Yeah.
know?
And they're evolving at a time where it's very difficult to survive on Earth. It
Which
appears
brings
as if the most genetic diversity is occurring at the bottom of the ice age.
yeah.
And when we come out of the ice age, well, what happened this time? We were the only ones left. Does that mean at the end of this interstadial, after the catastrophe happens, 90% of the population is reduced? We all get stuck in little pockets on all the continents, and we're separated for a very long period of time, thousands of years before we build back the population. And when
Mhm.
that happens, each continent has its own new, completely different type of hominid.
And maybe that's a repeating cycle in and of itself,
Yeah.
right? Because one of the things that's noted is that the genetic diversity of Neanderthals was actually pretty limited, which would suggest that at some point they were kind of like genetically bottlenecked, maybe because of a geographical limitation, like you just suggested. Like perhaps we go through this on a regular basis where things get kind of whittled down, we get stuck in our own isolated pockets, and then the climate changes and everything opens up and genetic diversity can be reestablished.
Yeah, we meet everybody again and we start intermingling.
Right.
That does a number of things. It makes it makes our gene pool better, less susceptible to like major disease or other issues, or even changes in the biome that we talk about. Like during magnetic excursions, certain animals can't make it in a low field strength, especially those that echolocate, like they start running aground and killing themselves because they have no idea what's going on.
Right. So with more genetic diversity, that would give us more a stronger ability to adapt to different conditions as well.
Yeah, exactly. And so 100,000 years ago, the magnetic field is variable. It's pretty normal. It reaches a very high peak here before the Lechamp. And then right at the beginning of this mixing, which is right at the peak here, 50,500 is when we start mixing, and we mix all the way straight down this line, all the way towards about here. And so if we could blow that up into just the Neanderthal demise, this is the two pulses, major pulses between 50 and 41,000 years ago that caused, and you can see up here, different mass extinctions occurring along the way. So things are being eliminated as we drop down to the lowest bottom in at least 100,000 years. It's right here. And then the Neanderthal is completely gone. And it's just us.
It's so interesting because it's as if we knew that something was happening that could lead to our distinction or the Neanderthal extinction, and therefore we should interbreed in order to like save one of us. Like it kind of looks like that, doesn't it?
Yeah, right up here at this high field strength. Maybe this is the golden age of enlightenment. We don't know what that is. Up at 13 VADM. Look at where we are. We're down here in the lower states. We're probably around 5 right now, which means we drop much further, bad things will happen. But when they started interbreeding was like the highest field strength possible. I wonder what that does to our brains.
Right. Well, and then the timing, if the last golden age was 12,000 years ago, 12, 24, 36.
Well, I would say this is the golden age. This is the highest field strength. This is 14. So that would be from 19 to about 15,000 years ago. According to, if it's magnetic field strength, it would be right here at the peak. Because this doesn't happen again until over here, when we started interbreeding. Or could it be there's an offset of a little bit?
I mean, that could still be, right? Like that could be the beginning of the ascending golden age.
I wonder if there's a connection. But we're trying to look at that right now, aren't we?
Yeah.
Now let's take a look at that versus temperature. So this is the time at the bottom of the ice age. This is our current warm stadial here, right? We have to go all the way back here to get warm again. It's off the graph. This is literally the entire ice age right there, the last 100,000 year ice age. Look at what the temperature's doing. This is a nightmare.
Yeah.
Very hard to live here. And so this is when the populations are very low and very isolated.
Well, that's also when they're moving, which makes sense.
So the movements are occurring at the bottom, right here. See, they're pointing to bottoms for movement.
Yeah.
When things happen, it's when things are the worst or dropping down.
Yeah.
And here's the migration of fully modern humans 2 times. One time at 50,000. So at that 50,500, we're migrating. Isn't that weird?
Yeah.
And so we mix throughout all of this major temperature shifts. Look at this. That is like 8 degrees up, 8 degrees down. Wow. So it's just amazing how resilient humans are. The reason the population is so slow is because of this. It's so hard to live when things are shifting like that. Now it's like, stable.
Right.
And what's interesting is this is where we're all burning up here on the right side of the graph. You can clearly see there's 3 other times it was much warmer in the last 500,000. And I just wish academics that spew the anthropogenic global warming nonsense would just come on the show and talk to us about this graph.
I wish that they would just look at this graph, right? I mean,
Yeah.
we've said this many times. The intellectual dishonesty and irresponsibility by not simply just looking up the temperature graphs for the long geological time scale, that alone completely disproves anthropogenic global warming. That's all you have to do is look at these graphs and say, oh, there's something wrong with my theory. But no one will do that. And I don't know what they do. What happens when they stumble on one of these? Do they just ignore it? That's the dishonest part. The rest of it is just a lack of responsibility to just look. It's the same thing as claiming that there's a pole flip every 12,000 years, because if you look at the look at the data, it's clearly false.
Right. And if you just look at the carbon dioxide numbers for the last 100,000, which is this temperature graph,
Mm.
it is stable for this whole period of time. CO2 does not change. It's sitting at around 220 parts per million the whole time.
Mm.
And look at the temperature is shifting 8 degrees C every few thousand years.
Mm-hmm.
So clearly the temperature is not controlled by carbon dioxide if it remains stable throughout this entire ice age.
Right.
Complete lunacy.
Yeah.
So what's changing the temperature in here? So often.
Right.
So much. There is so little that we know about the complex solar system that we live in.
Mm-hmm.
And you can even see like interference patterns within this data set. There's clearly these two, whatever these two cycles are, they're probably being controlled by the same thing. This is probably the same cycle. This is it too. This is it too. That's it too. But sometimes it's two spikes. Sometimes it's noise. There is such a complex system that's happening here. I don't think we will ever have an explanation for what everything is, everything going on there.
Well, I think that the problem is, you kind of said it already. It's like interference patterns combined with the, what I've been saying a lot recently, which is like, we don't have the perspective. Like, we have to zoom out so far to really see. There's clearly multiple cycles going on, right? And then those create interference patterns. And it's very hard for us to see because we can't zoom out enough because our lifespans are so short. The only way for us to do that is to, collect all of this information and pass it from generation to generation to generation to generation, or preserve it somehow until, we reach the next golden age and then we just know everything. But I don't see that happening. We're too short-sighted even to collect that information in a way that can remain meaningful to look at it over, from the perspective of humans that came before us, tens of thousands of years ago.
Yeah, exactly. And take a look at this graph here. Right, look at these vertical lines. There's like there's one here, two, there's here. These are times where the temperature instantaneously rises 6 degrees or so.
It's so weird. Like, how does that happen? Like, what's causing that?
If delta T is degrees, it's actually shifting 20 degrees up and down instantly. So the only thing I think that could be is our sun. And we're looking at the variability of the sun here.
Well, and it would make sense that it is some kind of energetic pulse, not just because of the extremity of the temperature rise, but also the extremity of the temperature fall. Like, it literally looks like there's a huge input of energy and then it dissipates.
Yeah, but it takes
falls
3 or 4
off, but it doesn't fall off in the same way that the temperature rises.
It takes 3 or 4,000 years for it to dissipate each time.
Right.
That's about these spans. This is like a 5,000 year, 3,000 years. So it's like, wow, it's warm. And then it gets cold.
Yeah. Yes.
And this is about the length of the Younger Dryas catastrophe. It stays cold down here for like 2,000 years. And then it's warm. And then it drops down. And then it's warm. And then it drops down. Stays cold. And then it gets warm and stays cold. This graph is so mind-boggling. It's only 100,000 years. The last 100,000 years. This is the last 4 great years. or the last 4 precessional cycles. And you can't see 4 cycles in here. When you look at the temperature, no, you can't.
And every one of those spikes is so extreme the way it starts, which I mean, it leads me to think that it has to be our sun.
Yeah. Yeah, this is our sun.
This is the information that we were looking for from, the first study that we talked about today. What is the frequency of maybe superflares from our sun? And this might be the answer.
Right, because we're considering this last rise that took us out of the Ice Age here into the Holocene. Robert Schoch and others, they're all considering the end of the Younger Dryas here. So here's the Younger Dryas drop down. That's the cold. This is coming out of it, that this is a solar outburst.
Yeah.
So you got a solar shutdown and then a solar outburst to take us out. And the solar outbursts are happening about every 5,000 years. But we haven't had one for the entire.
So different? Why is this time period so different?
What do you mean?
Well, I mean, look at the graph. Like, we're not getting that up and down anymore. Like, why?
That only happens during the Ice Age. During the interstadial, it calms down. Yeah. So if you look at the last 400,000 years, the last cycle looks just like this.
Yeah.
And so they attribute many of these spikes to Dansgaard-Oeschger cycles. Have you heard of that?
I forgot about that. Yes.
Yeah. Dansgaard-Oeschger cycles cause this.
Can you explain that for our listeners?
Well, it's probably not true because it doesn't show up at the right periodicity here. The length of these warming periods and cooling periods vary from just about 1,000 years to thousands of years. And I think they've nailed, let me see if I can get a time frame. The Dansgaard-Oeschger is like 14.
I can't remember.
And they show the graph, and these are the Dansgaard-Oeschger cycles. 1470 is the cycle.
1470. Okay.
But it's debated because it's not consistent. So these rapid shifts are the Dansgaard-Oeschgers.
Yeah.
But they certainly weren't happening here. So this is the Eemian interstadial. This would be the piece that's not on our graph.
Mm-hmm.
The graph we've been looking at just starts right around here and goes to present.
Right.
But you can see at the bottom of the Ice Age, it's not just cold. It's pulsing the whole time insanely, which would make it impossible for any group of hominids to take a foothold in one area and grow. It would rapidly be destroyed and be completely different. You have to be migrating this whole time to survive. Going north, going south, going north, going south.
So that's really interesting because it suggests that the glacial periods really are the periods of increasing genetic diversity. It's the period where we're moving around and we're intermingling with other hominids. And then it's the warm phases or the stable phases, where the interstadial phases, where we potentially are much more isolated in our own pockets. That's not true right now, right? Because at the moment we're a global civilization. You would think it would be the other way around.
Yeah. It is antithetical that you would think that like during warm, completely quiet periods that diversity would flourish. But that's not what happens because I think the stability is so long that any species is stuck in its ecological niche. But if you shift the climate, that ecological niche is destroyed and that species either goes extinct or has to move and become something else. If you've got 10,000 years, generation after generation of the same temps, certain things do go extinct, and then other species that are there just fill the void. So you need less and less diversity for a stable place.
Yeah.
And so maybe mass extinctions occur during stable times as well.
Wasn't that interesting to think about?
But what's clear is that looking at the last here is 140,000 years down below here, this delta T. What I mean by that is they're showing this as a temperature graph, but it is the oxygen O18 isotope they're using here. And oxygen 18 isotope is the best proxy for temperature on Earth.
Hmm.
It's the 018-016 ratio that shifts directly with temperature.
It could also be that, because I was thinking about this earlier, like it could be that panspermia plays a role here in this genetic diversity, right? In the sense that an interstitial period being more stable potentially provides the opportunity for for certain genetics to do well, right? Like that could help explain why we have, let's say, parallel evolution of similar species like hominids or elephants or whatever it is. And so perhaps it is in the unstable phase where those genetics don't really have the opportunity to come to fruition because the conditions are changing so rapidly.
Yeah, and it's the increased cosmic rays at the bottom of these excursions. I
Right.
think that's driving the genetics. The only thing we know that mutates genes are cosmic rays. And so if
Right.
we want to get new species out of thin air, we mutate the species that exist.
Mm-hmm. Mm-hmm.
And that happens at these lows.
Right.
And so Robert Felix was right. Right?
Mm-hmm.
Evolutionary leaps
Mm-hmm.
and magnetic excursions. That's what's
Yes.
happening.
Yeah.
And it goes both ways because at the same time, we get massive die-offs of species that can't make it. The cosmic rays mutate existing species. And on the other side, we've got all new species forming the devoid ecological niches that were left from the extinct ones.
Yeah. I still find it completely fascinating that we intermingled with Neanderthals like in a specific time frame at least once, if not prior, but in a particular time frame just in the nick of time, basically, in order to preserve some of the Neanderthal DNA, as if we knew what was coming.
Yeah, and maybe without that mixing, we wouldn't have made it either.
Well, I'm wondering about that too, right? That 2% of remaining, well, no, that's not true, right? Because we do have sub-Saharan African populations that have no Neanderthal DNA.
So the
They
whole
have
Earth,
other DNA that we don't even know what it is. They have a ghost DNA, and it's a
right? So if
significant
we didn't make
percentage.
it, the planet would all be sub-Saharan Africans.
Yeah,
We got lucky.
supposedly. Yeah.
Great show.
Yeah. Do we have a bumper?
No, no,
We
they
don't get
don't.
no bumper
That was the whole
today.
problem.
Right.
There was no bumper. Guys, you can
Find us
rewatch the show tonight on where is it?
Magnetic Reversal News at 8 p.m. Mountain Time on YouTube.
And don't be scared, be prepared because everything we talk about here is not fantasy and science fiction. It's all happened in the past and it's all going to happen once again in the future. It's really weird to do this.